In this video, we're diving into the creation of what I'll call a Toddler's Interactive Adventure Pod, an imaginative play space designed to spark joy and wonder in the heart of a courageous little boy. My 2-year-old nephew has faced incredible challenges, including open heart surgery. This project is more than just a gift, it's a testament to resilience and the magic of childhood exploration. This video explores the nuts and bolts of the construction, including woodworking, electronics, and programming. Longtime viewers of the channel know I have a passion for building and repairing video arcade machines and arcade controls. So that's where I started with my quest to make a gift for my nephew's second birthday party, because he loves cars and anything with switches or buttons. I found a local arcade operator selling a large assortment of driving controls. They're somewhat abused, but nothing that couldn't be repaired. I selected a control panel from the classic 1994 arcade game, Cruis'N USA. I got a great deal considering vintage controls can sell for a lot of money, and this control panel was complete with a force feedback motor, wiring harness, and all the switches. When my nephew's a little older, I figure we could turn it into a proper arcade machine. Here's a shot of the bare control panel, mounted to a wood frame I designed. It's constructed of 2x4s and 5/8 inch MDF. I stripped off the panel's black paint, and the bare steel looks really good, so I'm just going to apply food-grade wax, which will prevent the metal from rusting. The panel is mounted to the MDF with 5/16 inch stainless steel screws and T-nuts. The wood is just screwed together. Pocket screws are used for some of the butt joints. I added 3/4 inch aluminum angle between the top and the bottom of the control panel to enhance rigidity. I drilled holes and inserted grade 8 1/4 inch bolts, which will be used to secure the outer panels. Here's a SketchUp model of the pod. The front panel is hinged to allow for maintenance. Large 100mm illuminated push buttons are used for the yellow headlights and the red and the green strobes on the hood. Window-like openings have been incorporated into the side panels to evoke an automotive aesthetic. The pod is about 29.5 inches wide, or 75 centimeters. It's 34.5 inches long, about 88 centimeters, and it's 31 inches tall, about 79 centimeters. Here's the pod with the MDF cockpit firewall and the removable front panel mounted. Again, all the panels are mounted with T-nuts to afford easy disassembly. Delivery will require a 6-hour road trip. I routed holes to mount the 100mm push buttons flush. The sides are on. Notice how the T-nuts are slightly recessed. This will ensure a smooth finish for the laminate, which will cover all the exposed MDF. The pod is all ready for laminate. The chrome hinges are fitted, the 100mm illuminated push buttons are installed. I CNC'd a rounded rectangular opening with bolt holes in the firewall to hold the secondary lower control panel. Here are the panels laid out on high pressure laminate. The color is a high gloss primary yellow. The sheets are 97 by 49 inches, about 2.5 by 1.25 meters. I'm using a track saw with a 56 tooth carbide tipped laminate cutting blade with a thin kerf of 1.8 millimeters. It's a little over 1/16 of an inch. I put masking tape along the cuts to reduce the chance of splintering. Some sites recommend cutting with the laminate facing down, but all my cuts came out clean. Plus I leave at least a 1-inch margin around the laminate to make it easier to glue. The excess will be removed with a router and a flush trim bit. Here's the pod with the laminate installed. Unfortunately, I lost the footage of applying the laminate with contact cement and the flush routing, but there's a lot of laminate tutorials on YouTube. The frayed material on the edges is just the protective plastic film, which I'll remove at the very end. Chrome T-molding is installed to clean up the edges. It's 5/8 inch, or 15.9 millimeters thick. A slot cut router bit was used to cut a 1/16 inch or 1.6 millimeter channel in the center of the edges to accept the T-molding. To install the T-molding, you just line up one end with the bottom edge, which won't have any T-molding because it'll be on the floor. It's hard to remove T-molding without damaging the MDF channel, so take your time. Then just gently tap it in with a soft mallet. You don't want to use a hammer with a hard surface because you can chip the chrome coating. The T-molding should be held very tightly by the channel, but if you make a mistake or it comes loose, you can use some hot glue or wood glue to hold it in place. Here's the completed pod with the T-molding installed on all the exposed edges, including the insides of the windows. This clip's a bit out of sequence, as you can see by all the functioning illuminated switches. Most of the animated lighting effects are being controlled in software by Raspberry Pi Pico. This will be discussed in detail, but first I'll focus on the electronics and wiring, starting with the secondary control panel located under the Cruis'N USA. The control panel has a toggle switch, 12 push buttons, and 6 rocker switches. Two of the rocker switches are 3-position. There are 3 5mm LEDs in orange, magenta, and turquoise, one vintage jeweled red pilot, 2 8mm RGB LEDs, one's auto-fading, 3 of the push buttons are illuminated, and there's a white OLED display. I designed the control panel in PowerPoint because I give a lot of presentations. There's probably better software, but it works, it's easy, it's in color, it's to scale, it's easy to overlay the whole cutouts, and when the layout's finalized, I was able to write a simple Visual Basic macro called extract shape info to export the coordinates and dimensions into my CNC software. The code loops through all the shapes on the slide. It has slightly different logic for circles and rectangles. The data is parsed into comma-delimited format. Memory is reserved to hold the data. Then the data is passed to the clipboard. I'll go ahead and run the macro. The data is sent to the clipboard, and here's the data. Here's my Romex CNC router cutting out the secondary control panel from a sheet of aluminum 1/8 inch thick, about 3mm. It makes easy work of the switch rectangles, the triangular push button, the display cutouts, bevels, and the rounded corners. Here's the cut panel. I used a random orbit sander with a high grit to get a clean brushed finish. Here's the back of the panel with the switches, push buttons, LEDs, and the display installed. The discrete LEDs are all hardwired, which just means they're controlled independently of the Raspberry Pi Pico, which will control everything else. The cathodes of the 5mm LEDs, the RGB fader, and the red jeweled LED are connected to ground along with 3 of the mini push buttons. The 8mm RGB LED on the bottom has a common anode which is connected to 5 volts along with a pin from each of the large toggle switches. The normally open pin on the top toggle switch is connected to the anode of the red jeweled LED in series with a 690 ohm resistor. Flipping the switch allows power to flow and illuminates the LED. The normally open pin of the bottom toggle switch is connected to the RGB fader in series with a 690 ohm resistor. This LED has a built-in circuit that automatically fades the LED through the colors of the rainbow. The bottom 8mm RGB LED has its red, green, and blue cathodes wired to the red, green, and blue mini push buttons in series with a 150 ohm resistor, a 300 ohm resistor, and a 90 ohm resistor respectively. The 3 remaining hardwired 5mm LED anodes are wired to the mini rocker switches. The other ends of the switches are wired to 5 volts with 690 ohm resistors in series. I chose all the resistor values by trial and error in an attempt to get even brightness levels. I also verified with a multimeter that the current doesn't exceed the maximums. Most of the LEDs are very efficient and you only need to run them at a fraction of their rated current. Here are all the hardwired switches and push buttons in action. It's very hard to film illuminated LEDs and accurately capture the color. In real life the lighting looks great and the colors are vivid and not washed out at all. The remaining 2 push buttons, 2 switches, and 2 illuminated switch LEDs are controlled by the Pico. Each push button and switch has a pole connected to ground, along with the button LED cathodes. The large round green illuminated push button has its anode connected to GPIO 6 on the Pico, with a 150 ohm resistor in series. When the pin goes high, the button will light up. The anode of the green metal push button's ring LED is connected to GPIO 7. This button has a built-in resistor, so it can be wired directly to the Pico. The normally open poles of the black mini push button and the green metal ring push button are connected to GPIO 10 and 11 respectively. When they're pressed, the GPIO pins will be pulled low to ground. The 2 3-position rockers are connected to GPIO 12 through 15. They'll be used to set the mode of the headlights to off, on, or blink, and the red and green strobes to off, on, or breathe. The Raspberry Pi Pico has 26 exposed GPIO pins, but this project will require 48 GPIO pins to control all the switches, lights, and peripherals. Therefore, I'm using a SparkFun SX1509 I2C I/O expander. The SX1509 provides 16 level shifting bidirectional GPIO pins with programmable pull-up or pull-down resistors. You may be thinking that these 16 GPIO pins combined with the Pico's 26 GPIO pins will still only provide 42 of the necessary 48 pins. However, the SX1509 has an on-chip keypad scanning engine that supports up to an 8x8 matrix of 64 inputs. Therefore, I can use half of the pins for a 4x4 matrix of 16 inputs and still have 8 inputs left over for LEDs. This is equivalent to 24 GPIO pins. The SX1509 is a built-in LED driver, which offers pulse width modulation, blinking, and a special effect called breathing, which smoothly fades an LED on and off. Furthermore, each GPIO pin can sink 15 mA of current with no cumulative limit. The SX1509 operates between 1.2 and 3.6 volts, so it's a great match for the Pico. You might assume that a keypad engine needs a matrix keypad, but you can achieve similar functionality using discrete inputs. For instance, instead of a common ground, 4 of the control panel push-button switches have one pole all connected to a common column 10, while the other poles are wired to the 4 individual keypad rows 0 to 3. This setup mimics the row and column structure of a matrix keypad, allowing the keypad engine to function correctly with individual push-button switches. Next, the 3 remaining push-buttons have a pole connected to column 9, and the other poles to rows 0 through 2. The unused row 3 will be reclaimed on the arcade control panel. The pod has 4 100mm illuminated push buttons mounted on the hood and grille. They act as lights and buttons. The Cruis'N USA panel has 3 illuminated rectangular push buttons, red, white, and blue, and 2 standard arcade buttons, yellow and green. The yellow arcade button is connected to the expander's remaining row 3 on column 9. The green button and 3 rectangular push buttons are connected to rows 0 to 3 on column 8. The 4 100mm push button inputs are connected to rows 0 to 3 on column 11. That uses up all 16 inputs on the keypad matrix. In order to simplify the wiring, I created a small keypad matrix PCB. It has 2 inputs for the Cruis'N USA control panel, so I could reuse the existing 12-pin and 5-pin connectors. I want to keep the harness original to simplify any future conversion back to an arcade cabinet. The 3 other connectors are for the other 3 columns of inputs. There's a single 8-pin output for the 4x4 matrix on the SX1509 expander. I etched the board myself using muriatic acid and hydrogen peroxide. The etching notes are available on my website. The LED bulbs and the arcade push buttons are all 12 volts, so they can't be powered directly from GPIO pins. Typically, you could use MOSFETs or transistors to drive the LEDs, but a more elegant solution is to use the ULN 2003, which is an integrated circuit featuring 7 Darlington transistor pairs with built-in flyback diodes, designed for driving high current loads like motors, relays, and LEDs directly from a digital logic circuit. It's inexpensive and simplifies the design by reducing the number of parts. The ground pin on the ULN 2003 is connected to the ground pin on the SX1509. The anodes of each LED bulb and the rectangular push buttons are connected directly to 12 volts. The expander's pins 12, 13, and 14 are linked to the ULN 2003's pins 1B, 2B, and 3B respectively. The corresponding pins 1C, 2C, and 3C on the ULN 2003 are then connected to the cathodes of the push buttons. When a pin on the expander is set high, then the associated pin on the ULN 2003 will sink current and light up the LED bulb. 12 volts is also connected to the anodes of the 100mm push button LEDs. Then pins 4, 5, 6, and 7 on the expander are connected to pins 7B, 6B, 5B, and 4B on the ULN 2003 respectively, and the 4 corresponding C pins are wired to the cathodes of the push buttons. Pin 15 on the expander is wired directly to the triangular arcade push button LED anode. I replaced this bulb with a more efficient LED so it can be run directly at 3.3 volts. The cathode goes to ground. When the expander pin goes high, it'll source current and illuminate the LED. At 3.3 volts, the LED bulb does not require a resistor and won't exceed the 8 mA maximum per pin source limit of the expander. The last 2 controls are the analog steering wheel and the 4-speed gear shifter. One terminal of the wheel's potentiometer is connected to 3.3 volts on the Pico. The pot's wiper is connected to GPIO 26, which is one of the Pico's 3 ADC pins. The third terminal on the pot is connected to ground. Turning the steering wheel should vary the voltage on the ADC between 0 and 3.3 volts. One pole from each of the gear shifter's 4 microswitches is connected to GPIO pins 16 through 19. The other poles are connected to ground. When the shifter changes gears, the connected pin on the Pico will be pulled low. Since only one gear can be selected at a time, it would be possible to save one GPIO pin by using OR gates to convert the 4 gear positions plus neutral to a binary number 0 to 5, which only requires 3 bits or 3 GPIO pins, but the added complexity would only be worth it if I ran out of GPIO pins. So that's it for the inputs. Now let's take a look at the outputs. The Cruis'N USA control panel came with a woofer and a tweeter. The woofer is in bad shape. You should not be able to see light through the cone. I'm going to replace it with this poke woofer that I salvaged from an outdoor speaker, circa 1997, but it looks like new. The tweeter that came with the control panel is also shot. It may not show up on the camera, but the diaphragm has a big gash in it. I'll have to find a replacement. The control panel also came with a crossover, which has been potted with glue for waterproofing. Only the fuse is exposed. I 3D printed a mount to attach it inside the pod. A JQ6500 module will be used to drive the speakers and play MP3 files. It's the same board I used in my ESP32 touch and sound tutorial.
I'll be back.
The board is controlled by a serial interface. GPIO 8 on the Pico, which is UART1 TX, is connected to the RX pin on the JQ6500. GPIO 9 RX is connected to TX. A 3.3 volt pin is connected to VCC, and the grounds are connected. The crossover splits the audio signal into 2 frequency bands, directing high frequencies to the tweeter and low frequencies to the woofer. The speaker output plus and minus pins on the JQ6500 are connected to their corresponding input pins on the crossover. The crossover outputs are wired to the tweeter and the woofer, being careful to match the polarity. I believe the JQ6500 has 4 MB of built-in storage for MP3 files. To load the files, you just plug the module into a Windows computer. It'll show up as a CD drive. You open the drive and run the one sketchy-looking executable file. The app doesn't support English, but it's straightforward. You click the second tab and click the one button, which I assume is Browse. Navigate to the folder with your MP3s, highlight all the files you want to upload, and press Open. The files then show up in the list. Go back to the first tab and click on the one button, which I assume means Upload. The progress meter will let you know when it's done, and that's it. The last electronic component is the SSD1309 OLED display on the lower control panel. This is the same 2.42-inch monochrome display that I used in my Caller ID project. It has excellent contrast and a wide viewing area. It's only 128 by 64 pixels, but that should be plenty for this project. It runs at 3.3 volts, so it can be powered by the Pico. It can communicate by either I2C or SPI. However, SPI will give you better performance, especially for any animated graphics. Wiring the display to the Pico is very easy. The display's CS pin goes to GPIO 5 on the Pico. DC goes to GPIO 27. Reset goes to GPIO 28. SDA goes to GPIO 3. SCL goes to GPIO 2. VCC goes to 3.3 volts. The grounds are connected, and a 100 microfarad capacitor is placed between VCC and ground to prevent brownouts on the Pico. There's a lot of wiring between the Pico, the MP3 module, the I/O expander, the transistor array IC, the display, and all the controls, so I designed a main PCB to simplify the wiring. It will hold all the breakout boards, the IC, a 5-volt regulator, and headers and terminals for all the inputs, lights, and display. Here's the PCB. I outsourced the fabrication because I didn't feel like drilling 150 holes, and there's a lot of small text which really isn't suitable for the toner transfer method. Here's an original Raspberry Pi Pico, no Wi-Fi. It gets plugged into the board. Here's the JQ6500 MP3 module. It snaps in too. Here's the SX1509 I/O expander. I had to clip one of the corners off because I made the tolerances too tight near the terminal blocks. Here's the ULN 2003 Darlington transistor array IC. It gets installed into a dip socket. Machine sockets are more reliable than the pressed ones, but you have to be careful because it's easy to break a pin. You need to get all the pins aligned just right before you press down hard. I didn't test my design before sending it out for fabrication, and there are a few corrections. I didn't have time to wait for a replacement, so I made a few hacks. You can see I removed a resistor because I changed an LED to a push button. I removed 3 pins from the display header. I was initially going to run the display using I2C, but the performance was too slow, so I switched to SPI. I soldered on 3 wires for the MOSI, clock, and CS on the Pico SPI 0 bus. I diverted the LED that I switched to a button to free up the CS pin. I also incorrectly chose a pin that doesn't support ADC for the steering wheel. I cut the ADC trace and rerouted the connection with this purple wire to GPIO 26, which is ADC 0. Okay, that takes care of the hardware. Now let's take a look at the software. Here's the MicroPython project in VS Code. The audio folder holds 22 sound effects that were loaded into the JQ6500 MP3 module. The fonts folder holds a single monospaced font called Unispace. It'll be used on the display to show the current gear. The images folder contains a splash screen that has been converted from PNG to the required mono format. It'll display when the program starts or when the green arcade button is pushed. I wrote a MicroPython serial library to drive the JQ6500 MP3 module. It's available on my GitHub site with examples on how to use it. I also wrote a driver for the SSD1309 OLED display. It's also on my GitHub site with lots of examples. I also wrote a driver for the SX1509 I/O expander based on a library provided by SparkFun. It's on my GitHub site with examples. The XGLCD font file is part of my OLED display library. It affords drawing text using fonts that can be converted from TrueType using a free utility. The main program is called car.py. Here's the import section. Array is imported to provide polygon coordinates which have to be unsigned short integers. GC is Python's garbage collector, which can be manually evoked to free up memory. My JQ6500 MP3 driver is imported. From machine, ADC is used for the analog input, I2C for communication with the expander, pin for control of GPIO pins, and SPI to talk to the OLED display. From math, a few trigonometry functions are imported to calculate polygon coordinates. From MicroPython, const is imported to declare constants, which helps optimize memory. My SSD1309 OLED display library is imported. My SX1509 I/O expander library is imported. From time, sleepms is imported for short delays. And my XGLCD font library is imported to draw text on the display. A little class called Light Mode acts as an enum to define the three states of the 100mm LEDs, either off, on, or blink. The main car class handles all input and output functionality for the pod. Several constants are defined. The OLED display will have a triangular gauge indicating the steering wheel position as defined by radius, base, height, number of positions, angle span, ADC GPIO pin, and a hysteresis threshold to smooth transitions between positions. The GPIO pins for the two push buttons not on the expander are defined. The 4 GPIO pins for the gear shifter are defined. There are 4 GPIO pins for the two 3-position rockers that control the 100mm LEDs. There are 8 GPIO pins for the 8 LEDs controlled by the I/O expander, and 2 GPIO pins for the 2 LEDs controlled directly by the Pico. GPIOs for the display's SPI bus, CS, DC, and reset are defined. Constants are set for the keyboard engine, rows, columns, sleep time, scan time, debounce time, and cycles before a release is registered. Keymap is a 2D list where each item represents the name of the button in the keypad matrix, organized by row and column. A dictionary process map defines what each button press does. All button presses have an associated MP3 sound effect, and some trigger LEDs too. A list of sounds holds the MP3s stored on the JQ6500. The list index +1 equals the JQ6500 file index, which is used to play the sound effects. Here's the constructor for the car class. Addictive triangle coordinates will hold all the possible combinations for the position indicator of the steering wheel. It's more performant to do all the trigonometric calculations once and store the results rather than calculate them every time the steering wheel moves. A for loop iterates through each steering wheel position and calls the calc triangle vertices function. This function first gets the angle for the given position number, then XY coordinates for the apex, the base left, and the base right are calculated. The results are returned as an array of signed short integers because that's what the frame buffer class expects. This optimization should give the smoothest animation on the OLED display. Next, the constructor declares prev wheel, which will store the previous steering wheel position. An ADC is initialized to poll the steering wheel pod. The 12x24 Unispace font is initialized. The SPI bus and the SSD1309 display are initialized. The JQ6500 MP3 player is initialized. The gear shifter's 4 GPIO pin inputs are initialized, and a variable prev gear will keep track of the previous shifter's position. The rocker switch's 4 GPIO pins for the headlights and strobes are initialized, and prev headlights and prev strobes will track the previous states of each. The I2C bus and IO expander are initialized. The 4 GPIO pins on the expander for the headlight and strobe LED lamps are initialized. A method called initialize LEDs is called. This method loops through all the push buttons in the process map dictionary. It retrieves the GPIO number. GPIOs between 1 and 7 are on the Pico. The pin class is called to set them as outputs with the initial state set to off. GPIOs between 12 and 15 are on the expander. The pin mode method is called to set them as outputs, which should default to off. Next, the constructor sets the GPIO pins for the black mini and green ring push buttons as inputs with pull-up resistors turned on. Variables to track the press state of each button are set to false. Prev key data tracks the previous value of the keypad data, and release count tracks how many cycles a button has been pressed. Finally, the keypad engine on the expander is initialized and passed the constants for rows, columns, sleep time, scan time, and debounce time. A method called Hello Bradley displays the splash screen on the display. GCcollect is also called to free up memory before the large image is loaded. Here's the main program logic. It starts by displaying the splash screen image. After 500 milliseconds, it plays a greeting sound effect, followed by a longer 3-second pause, after which the display buffers are cleared. I'll demonstrate the splash screen.
Hello, Bradley.
Here's the main program loop. The steering wheel indicator on the display is cleared by drawing a black filled rectangle over it. A circle is drawn to enclose the indicator. The steering wheel potentiometer is read, which returns a 16-bit value. The old pot has quite a bit of jitter. I tried cleaning it, but the results were still erratic. If this were an actual gaming cabinet, I'd replace the pot. A small capacitor might also suffice. However, I was able to mitigate the noise in software. Movement is only registered if the absolute value of the 16-bit ADC value minus its previous value is greater than the hysteresis threshold. This ensures that the indicator doesn't move unless the steering wheel actually turns, and it prevents the indicator from oscillating when the wheel is near the boundary of two adjacent positions. When a valid movement occurs, the 16-bit value is scaled to a number between 0 and 16 to correspond with the 17 possible indicator positions. A min statement is used to catch any errant readings. Then the previous wheel position is updated to the current position. I just noticed a possible bug. Looks like I forgot to initialize wheel scaled. This should have been done outside the main loop. I think an error could be thrown if the machine is turned on with the wheel in the 0 position. Anyway, the associated coordinates are retrieved from the triangle chords dict, and the draw polygon chords method is called to draw a filled triangle on the display. Here you can see the triangular indicator on the OLED display turns with the steering wheel as it's rotated. Next, gear is defaulted to N for neutral. The 4 shifter micro switches are read, and the gear variable is set to 1, 2, 3, or 4, assuming the stick is in gear. The draw letter method is called to draw the gear number on the display. If the current gear does not equal the previous selected gear, and the gear is not neutral, and the gear is valid, then a gear change sound effect is played. The previous gear variable is updated to the current gear. Display present is called to actually update the OLED display. Here's the gear shifter in action.
2, 3, 4, 1.
Next, the rocker switches for the headlights and the strobes are read. Since they're 3 state, the values are added and the results will be 0 for off, 1 for on, and 2 for blink or breathe. If the strobe state doesn't equal the previous state, then the previous state is updated. And if the strobe's value is equal to on, then the expander setup blink method is called with all zeros, which cancels any blinking and sets the LED on. Else, if the strobes are in the blink or breathe state, then the expander breathe method is called, which creates a smooth fading effect on the LEDs. Otherwise, the rocker is in the off position, and the LEDs are turned off by calling setup blink with all zeros except for the on intensity, which is set to 255. Identical code is used for the headlights, except the expander blink effect is used instead of the breathe effect. This just continuously toggles the headlights on and off. The strobe's rocker is switched from the off to the center on position. Now it's switched to the breathe position. The headlights rocker is switched on. And now it's switched to the blink position. Next, the keypad engine is red and returns the key data. If the key data doesn't equal the previous key data, and the key data isn't 0, then a new button press has occurred. The previous key data is updated to the current, the release count is set to 1, the row and column of the keypad matrix are retrieved using the getRow and getColumn methods, and a method called processInput is called and passed the name of the key that was pressed. Unfortunately, the SX1509 doesn't have a built-in way to check if a key is released. You can use the scan time and debounce time to avoid noise and chatter, but if someone holds a key down, then it'll keep registering button presses, and in the interim, the key data can be 0. So here's my approach. If the previous key data doesn't equal 0, it means a button was previously in a pressed state. If the key data is now 0, then it could mean a release, but we can't be sure until the scan time expires, so the variable release count is incremented. If the key data doesn't equal 0, then someone's definitely holding down the button, and release count is reset. If the release count is greater than the maximum release count, which is greater than the maximum number of cycles for the scan time, then previous key data is reset to 0, which indicates the keypad is now in a release state. This software-based approach works well as long as you have the max release value dialed in right. Next, the 2 push buttons that are not part of the expander keypad are pulled. I wrote my own method to bounce the push buttons. The pin number of the black mini push button is passed to the read to bounced pin method. It will return 1 for high, which is not pressed, and 0 for low, which is pressed. If the button is not pressed and the black mini pressed variable is true, then the button was pressed but it's now released, so black mini pressed is set to false. Else, if the button is pressed and the black mini pressed is false, then we have a new button press. The process input method is called and passed the name of the push button that was pressed. It's not very dry, but the exact same code is run again for the metallic green ring push button. I think I did it this way because I thought the button might need a different debounce time. Regardless, it could still be refactored using a loop. So that's the end of the main loop. It sleeps for 10 milliseconds and repeats. The play sound method is used to play MP3 sound effects stored on the JQ6500. It's wrapped in a try statement to catch any errors. The index of the past sound title is returned from the sounds list and incremented by 1 because the JQ6500 index is 1 based instead of 0 based. Then the player play by index method is called and passed the index. I really like this module because it's so easy to add sound to your project. Here's the process input method. I just noticed the docstring is wrong. It does handle sound effects for button presses, but it also handles any associated LED effects and more. A variable process retrieves the sound effect and the LED effect if applicable. The sound effect is stored in the effect variable and then passed to play sound, which plays it. If there's an LED effect, it's stored in the variable LED. If LED has value, then setLEDState method is called to update the LED. In the special case that the sound effect equals Hello Bradley, then the Hello Bradley method is called, which displays the splash screen on the display for 3 seconds. Read to bounced pin is just my custom method to debounce a pin. It's passed a GPIO pin and an optional debounce time, which defaults to 50 milliseconds. The GPIO pin is sampled twice at an interval equal to the debounce time. The last value is returned as long as the 2 samples are equal, otherwise none is returned. Here's the setLEDState method. It takes a GPIO pin number and there's an optional off variable that can be used to force an LED off. If the pin number is less than 10, then it's on the Pico. A variable LED is set to the GPIO pin as an output. If the optional off variable is true, then the LED is turned off. Else the LED is toggled. If it's on, it's turned off, and if it's off, it's turned on. Otherwise, if the pin is greater than or equal to 10, it's on the expander. A variable ROF stores the off time intensity register for the given pin, and RYON stores the on intensity register for the pin. Then the LED is cycled to the next state. If ROF is greater than 0, then the LED is currently breathing and should be turned off. This conditional block also fires if the optional force off parameter is specified. If RYON is greater than 0, then the LED is currently off and should be turned on. else the LED is on and should be switched to the breathe state. A main guard is inserted to allow running the script directly. A car class is instantiated. A try statement is used to catch errors and allow for a graceful exit. The car's main method is called to run the program. Control-C is caught to exit, and the finally statement cleans up the display, the expander, and turns off the LEDs connected to the Pico. Okay, that's it for the code. I'll do a quick demonstration of some of the push buttons. I hope you found this video helpful. There's a full write-up on my website along with all the code, CAD files, schematics, and wiring diagrams. The link is in the video description. You can support this channel by subscribing and leaving a like. Thanks for watching.